These are the notes for section 2.1, talking about the tangent and velocity problems. The goal in this section is to find an equation for a line that is tangent to a curve. In particular, we're going to be looking for the equation of the line tangent to the graph of y equals x cubed at the point 2, 8. So first of all, let's look at some pictures to describe what it is we're trying to do. So here's a graph of y equals x cubed, and next to it is a line that I've drawn tangent to y equals x cubed at the point 2, 8. Our goal is to find the equation for that line. To find the equation of that line, we need the slope of it. But before we can do that, let's talk a little bit about what a tangent line actually is. Here's a picture of y equals x cubed, and the red line is what's called the tangent to that curve at the point 2, 8. So right here at 2, 8 is where that curve touches. It just barely grazes the line. Now, if we zoom in a little bit and look a little closer, same point, 2, 8, which is right here. We're looking at that red line and the green being the graph of y equals x cubed, and you can see that the tangent line is approximating that curve. We look a little closer yet, same point, 2, 8. The green and the red become even more alike. So tangent line is often also associated with the slope of the curve at a point. So then the question becomes, how do we find that slope? Well, to do that, what we're actually going to look at are secant lines. In this diagram, we have a number of lines hitting the graph of y equals x cubed at 2, 8. So here's our point right there. Okay, the red line is the tangent line. The tangent line, like we saw before, just grazes the curve at one point. These other lines, the blue and the orange, are what are called secant lines. And they're actually going to, as you get close to this point 2, they're going to hit them at 2 points. So the blue one hits down here close to 1 and at 2, 8, and the orange one's hitting a little bit closer to 2 at more like 1.4 and at 2. The idea here is to look at what's going on with secant lines as we move our x value closer and closer to 2. So you get the idea that there's going to be a limit involved here eventually. But we're wondering what's happening to the slope of the secant lines as the secant looks more and more like the tangent. Whatever that limiting value is, that's what we'll take as the slope of the tangent line. So let's go back to the notes. So we're looking for the slope of the secant line given these 2 points, 2x and another point that's just any random point on the curve x cubed, where the x value is x, the y value is x cubed. So we know to find the slope, we take the difference in the y's over the difference in the x's. So then what we're going to do is let our graphing calculator find a table of values for us based off of this equation. If we just plug it into our y1 of our graphing calculator, and then what we're going to do is look for some numbers that are close to 2, or numbers as we approach 2. And we do that, first, like if we plug 1 in, you're going to have, remember it was x cubed minus 8 over x minus 2. If you plug 1 in, you're going to have a negative 7 over a negative 1, which is going to be 7. Well, if we let the graphing calculator do it, and you can do that really easily if you put your calculator on ask for a table, and you can just plug in your values. I can show you that in class. But if we do that, then the values fill in as 9.25, 11.41, 11.94, and 11.994. Now that's as we approach 2 from the left. Here we're going to be approaching 2 from the right. And if we fill those values in, they'll look like this. It's pretty obvious from the table that as we get closer and closer to 2, the y values are going closer and closer to 12, no matter which way you're approaching it. They both seem to be going to 12. So in this case, we would say that the slope of the tangent is the limit as x approaches 2 of the slope of the secant line, which it appears from the table is 12. Then once we know the slope of the tangent, we have a point, we have a slope, it's easy to find the equation of the line. We just say y minus y coordinate is equal to my slope times x minus my x coordinate, and if we solve that for y equals mx plus b form, it's y equals 12x minus 16. Now we can alter the problem just a little bit, and instead of having just a general function, if we say that our function is actually a position function, and we're talking about position graphed over time, then when we look at the secant line slope, what we're really doing is looking at a change in your position, which is what's going on the y-axis, the change in position over the change in time, which sounds a lot like velocity for those of you that have taken physics. So let's go back to the notes and look at that idea. So if we look at the slope of the secant line between these 2 points, then it's the change in the y, which is s of t2 minus s at t1, over the change in time, t2 minus t1, which actually represents the average velocity. So it's that slope of that secant line, average velocity. But if we take the limit of that as t2 approaches t1, we let t2 get closer and closer to t1, and that secant line will look more and more like a tangent line. So that limit represents the velocity at a particular point, which we would call the instantaneous velocity. If we go back to our position function diagram and change things just a little, so that instead of calling our points T1 and T2, we call them T1 and T plus H, where H is just a small change in our x value. Then our y values become s of t and s of t plus h, and that will change our equation just a little bit. Now when we go to find the slope of the secant line, our change in our y's, which is right here, is s of t plus h minus s of t, and our change of x is, well, t plus h minus t, which turns into h. So our formula becomes a little bit different. So the average velocity formula becomes the change in y over the change in x, s of t plus h minus s of t all over h, and the instantaneous velocity is the limit of that, and this time we're taking the limit as h goes to 0, because as h goes to 0, those 2 points would get closer and closer together. Like so. So the rest of the notes are an example of this kind of problem where we've got an equation that's given to us for our position function. Some of you in physics might recognize this, the negative 4.9 t squared, the acceleration due to gravity, half of that, and then your initial velocity times your time, and we're given that our initial velocity is 10 meters per second. So s of t is the height of the object when it's thrown into the air. We want to find the average velocity for the time period beginning when t equals 1 and lasting, and we're going to do some various lengths of seconds, 0.5, 0.1, 1/100th, and 1/1000th of a second. The idea being that if our time period is getting smaller and smaller, the time period is our h value. So these are our h's, and we're letting our h's go to 0. So, keeping in mind that our average velocity is found using this equation, okay, we're going to apply it with s being that function. So, if we plug that function in, then we have 10 times t plus h minus 4.9 times t plus h quantity squared, and then minus s of t, which is 10t minus 4.9 t squared. And then all of that is divided by h. So if we do a little bit of algebra expanding that out, we're going to have a 10t plus a 10h minus the 4.9 will be multiplied by a t squared, and then the t plus h times the t plus h, you're going to have 2 of those, times the 4.9 is going to be a minus 9.8 th, and then h squared times a negative 4.9, so minus 4.9 h squared, minus 10t, and then plus a 4.9 t squared, all over h. Then what we're going to do is look for things that we can cancel out here. So let's see, we've got a 10t and a negative 10t. Those cancel each other out. We've got a 4.9t squared and a 4.9t squared, positive and a negative, so they cancel each other out. So the only terms left are this positive 10h, this negative 9.8th, and this negative 4.9h squared. They all involve an h, so we could actually cancel an h. Let's do that with a different color. Cancel an h in each of them, so this h can cancel with that, that, and the one that's squared up here. So now all I have left for my final function is a 10 minus a 9.8t, the h was gone, minus a 4.9h. Okay, and now what we're interested in is when t equals 1. Okay, so then this function when t equals 1 becomes, so let's remember what we had here. We were looking at the average velocity. So v average at t equals 1 becomes so v average equals 10 minus 9.8, because we're letting t be 1, minus 4.9h. So we simplify that, we have 0.2 minus 4.9h. And now what we're going to do is plug in these different values of h to that and figure out what our average velocity seems to be going to as h approaches 0. So all we have to do is plug this into y1 in our graphing calculator and then create a table, and the results are going to look like this. So I filled in those values on the table, and if we look at as h goes to 0, it appears that the average velocity is going to 0.2. So when it says estimate the instantaneous velocity when t equals 1, we're going to say that that's the limit of the average velocity as h goes to 0. So the instantaneous velocity, we're going to say, appears to be 0.2. And since that's velocity and our units are meters and seconds, it's meters per second. Then for an alternative approach would be to use the formula, the other formula for the average velocity, which didn't involve the h approaching 0, but the 2 times approaching each other, time 2 approaching time 1. If we use that idea, keeping in mind that we were trying to get closer and closer to 1, because we were interested in at t equals 1, then our average velocity would look more like this. S of, instead of t2, let's just call it t, minus S of, instead of t1, let's just call that 1, the value we're approaching, all over t minus 1. Okay, if we do that and we plug it into our formula that we had originally, S of t, remember, was 10t minus 4.9t squared minus, now we're plugging 1 into that formula, so 10 times 1 minus 4.9 times 1 squared, all over t minus 1. So simplifying that just a little bit, we end up with a negative 4.9t squared plus 10t minus 5.1, all divided by t minus 1. So that's our average velocity. And if we plug that into our y1 of our graphing calculator and ask it to create a table of values, I'm just going to put in a few values. I'm going to look at t as 1.5. Remember, we're getting closer and closer to 1, so I'm going to approach 1 from the right here and look at values that are closer and closer to 1, like these, and the y values that correspond look like this. And so these numbers should look familiar. They're the same as the ones in the previous table. So it's obvious that as t approaches 1, the average velocity is approaching 0.2, which was the same answer that we got before. And that's it.